morning. We begin lecture 45. Again, thank you very much for the cooperation extended yesterday so that we could cover lecture 43 and 44. So since we have covered more material than a typical lecture, I thought it would be good for us to summarize the key concepts. But as you are seeing in CDMA, it's several simple concepts that have been put together to build a very complex, very efficient system. So maybe even to begin with, if I were to ask you to draw the block diagram of a spread spectrum system, multi-user spread spectrum system, based on the concepts that we have already studied so far, I think that would be a very good exercise. So this is how it would go. So for user 1, you would have the information bits. This is user 1. And you would map it onto a symbol. That would be exactly as you would do for a narrowband system, bits to symbol mapping, depending upon what the constellation modulation you're using. We have been looking at the binary as a simple form, but you don't have to limit yourself. Then would come the process of spreading. Okay. So the introduction of chips. So let's assume that it's a binary modulation. So the process of spreading introduces more signal transitions. Okay. And then after that you will do the pulse shaping, okay. And we have combined these two operations quite often to refer to this as our spreading operation, but that's okay. There is a bit level spreading and then there is a pulse shaping that is associated with that. Okay, so this can also be broadly classified as the spreading process. Okay. So at this point our signal will enter the channel. The channel can be a multipath channel. So multipath, so it could be time varying and time dispersive. Okay, so that is part of our, now where does the interference from other users come in? So the our signal has experiencing some channel, add to it the signals of other users. So basically you would have several of them. Each of them will, if they are spread spectrum, they will go through similar operations. They will go through their own channel, okay, and then will get added on to our. So basically you will have several of these interfering signals that are getting added to that. And to all of this we have the AWGN that will always be present. AWGN is present. So here is a system where there is signal which has been spread, many user signals which have also been spread that are mixing together in the channel, causing potentially causing interference, and AWGN also present. Okay. Now at the other end, the first step will be the match filter. And this would be a chip level match filter because that is how we want to be able to separate. After the chip level match filter, then you can do the despreading operation. Okay, despreading operation. But because we have also encountered other impairments such as time varying dispersion and other so we would also write down here, in addition to despreading, we would probably do some form of processing. Okay. The processing would be in the form, or processing would include interference suppression. I need to be able to handle all of the interfering signals, interference suppression. I would also need to worry about the time dispersion compensation, because only then I can apply the decision device. And if once I have done all of that, then comes the stage where I will do a decision and then take out the bits. Okay. So, at a high level, I do not want you to miss the where exactly is the spreading despreading operation. So, what we have been studying deals with spreading and despreading operations. Now, these operations do not require you to know the channel, but you need to be able to synchronize, because your spreading and despreading must be applied at the correct points and in a synchronized manner. Now, these two operations, interference suppression and time dispersion, it's not time, it's time dispersion compensation. So, some form of equalization. These will require you to have channel estimates. So, they will require accurate channel estimates. Channel estimates would mean the complex channel gain. So, basically magnitude, amplitude and phase is required. So, you are building a coherent receiver, channel estimates. Okay. And this is usually done in the case of CDMA 2000. CDMA 2000, that coherent channel estimates are obtained through a pilot channel, which is not transmitting any information, but is only transmitting an M sequence, so that you can do the channel estimation. So, there is a pilot channel, and in WCDMA it is a combination. There is a pilot channel plus pilot symbols. Pilot symbols are nothing but known symbols that are inserted in your traffic sequence. Okay. Now, in today's terminology, when we design a coherent receiver, you have to transmit known symbols, right? Typically, you would have called it known symbols. Why do you call it pilot symbols? You know, the terminology is always pilot symbols. OFDM, these are the pilot symbols in the OFDM system. And the history comes from, because in the CDMA system, there was a channel which was dedicated for channel estimation called the pilot channel. So, anything associated with pilot channel estimation now seems to have the name pilot associated with it. We call it pilot symbols or a pilot. So, basically, there is a need for you to do very as accurate as possible channel estimation, and that is what we have seen. Okay. So, okay, I thought there was a question. The form of the receiver that we would like to work with is the chip match sequence, followed by the despreading operation, and of course, along with that, whatever additional processing that we would need to do. Okay. The two properties that are very important for us, one is mutual orthogonality, that makes me robust against other users' codes, and self-orthogonality, and both of these are necessary for us to build a CDMA system. So, maybe just to re-emphasize, the mutual orthogonality is what helps me be robust against multi-user interference. The common notation is MUI, multi-user interference. Okay, this is the interference caused by other users who are on the same channel, multi-user interference. Okay, and self-orthogonality, this is the one that helps me deal with the multi-path, time dispersion. Time dispersion. So, those are the two impairments. As you can see, if you went to go back to the first channel, the things that we are worried about is the channel impairments and the interference impairment. So, both of these must be handled in the despreading and the processing operations, which is important for us. So, this is important, the two parts. Then we also said that we studied the properties of random sequences. Let me just write down the key results. Random sequences as a starting point for our understanding of choice of spreading sequences, and we showed the following properties, and basically we said that if we can achieve this type of performance, it's very good. So, the random sequences are XX of k, autocorrelation. This comes out to be delta of k, and that's a property of the, and cross correlation RXY of 0. This we said was a measure of the interference. because that's what comes in when I try to despread my desired signal. I will get a cross correlation between my sequence and the sequence of the interfering signal. So this is a measure of the interference, and we want to keep this quantity in mind, and we did a quick statistical characterization. This one we showed because of the information bits being independent. This one turns out to be zero mean, the property of the bit sequence that represents the random sequence, but more importantly, we were interested in the energy. So R x y of 0 squared, and this we showed was equal to 1 over q. And this is the one that tells us that if I can use something that has the properties or behavior like a random sequence, I get a suppression of my interference by a factor 1 over q. So if there are two users, two interfering users, the net interference that I will see is approximately 2 over q. If I have k users, it will be k over q. Okay, that's the net interference. So obviously, you don't want your k to become larger than q, because your protection against your interference is primarily dependent on q. So the way to start to think about the system is that this is a system that is very good at extracting your signal. In the process of extracting your signal, if you have good correlation properties, it will suppress the unwanted signals. And it can suppress any, when I say any number, it suppresses multiple unwanted signals at the same time. The single operation will suppress them, and it suppresses them by a factor of 1 over q, and that is what makes the system robust. Okay. We did spend some time talking about the properties of PN sequences. Again, these are basic shift register operations, so I'm assuming you would not have had any difficulty to generate this sequence of 15 values. Let me just summarize the properties, and I think that will be very useful for us, because even if you have studied M sequences before, these are very crucial for us to understand CDMA 2000 and wideband CDMA. So the properties of M sequences. Again, just a quick summary, since these are basic concepts. If I have M shift registers, that means I have a primitive polynomial in GF2 which is of order M. Okay, M shift registers. So this will lead to a sequence of length 2m minus 1. And interestingly, this also happens to be the period of the sequence, because after that the sequence repeats itself. So very interestingly, what we call as a PN sequence happens to be a periodic sequence. Actually, there is nothing, well, not nothing random, but it is a very predictable sequence after you have gone past one period. Okay, so very interesting. So, but it has all the properties that we are looking for. What are some of the other properties that we are interested? By the way, in the shift registers, we may be dealing with zeros and ones, but the mapping that we are using, a 0 will map to a 1 will map to a minus 1. So please, whenever we interpret the results, especially when we're doing correlations, we have to be careful. Are you doing it in the bipolar values or the binary values? If it is binary, you are doing modulo 2 addition. If it is the bipolar values, you're actually doing the multiplication. So again, keep that picture in keep that point in mind, so there's no confusion about the interpretation of the results. These M sequences have got the following properties. Again, just interesting for us to observe balance property. The number of zeros and ones are almost the same, and actually there is a very precise relationship. There are 2 power m by 2 ones and 2 power m by 2 minus 1 zeros. Okay, so once they get mapped, there's one extra minus 1 compared in the overall sequence once they get to the bipolar value. So otherwise, this is a good picture, because when I add any of these M sequences, the answer will be because of this property, I will always get the value. Okay, so there is a important indication of how these things are going to play out for us. So basically, the ones and minus ones will start to cancel each other, and I'll be left with a -1 at the end if I add this any of these M sequences. Okay, in the bipolar representation. The other interesting property is that when I take a M sequence and do a modulo 2 addition of itself with a cyclic shift of k units, cyclic shift, I produce another cyclically shifted version of the sequence. So all the properties are still preserved. The balance property, the run length property, all of that are still preserved. So basically, it's just a cyclic shift of that. So this is again a very useful property, as you will see in today's lecture. Okay, run length property, I won't rewrite that. It just says that the probability of having a sequence of identical digits 0, 0, 0 or 1, 1, 1 becomes less and less probable. So long runs are less probable. That's all, nothing more to add. Probably the most important, let me use a different color, that is going to be the autocorrelation property. And this is what we will leverage anytime we work with M sequences. So this basically says Rx of k. This is a cyclic autocorrelation, defined as 1 over q summation L is equal to 0 through q minus 1, x of L, x conjugate, we are dealing with real values, so conjugate really does not matter, L minus k mod q. Okay, and this is what we showed yesterday as -1 over q. And this is a very useful property because this is what will be the strength of the M sequence when we work in a environment where there are multiple users, okay, and multipath as well. This also led us to some observations that M sequences, basically all the different M sequences that are available are cyclically shifted versions of it. So there are some limitations for M sequences. There are limitations when there are multiple users, because then I have to give them all different codes, and actually these codes are not, they're all cyclically shifted versions. So therefore, there's a confusion when you have multiple users and multipath. There is a possibility that we will not be able to tell the difference, whether it's a new other user or it's a multipath component. So this basically says that, okay, if I assign one of the M sequences, then I cannot assign several cyclically shifts. So that's a limitation. So we also said that if I take sequences from different generator polynomials, M sequences from different generator polynomials, there are good sequences available, by the way. You can get good correlation, but you want large number. You want to have, let's say, 32 users, and in order to find 32 sequences from different generator polynomials, all of which have good correlation properties, is going to be the challenge. So different generator polynomials, here there is no guarantee of the cross correlation. So you have to check the cross correlation. So you have to check and see if the cross correlation is okay. Check the cross, and there are cases where you will see poor cross correlation, as we mentioned yesterday. Cross correlation. Okay, so that is a quick summary of what we have said as far as the M sequences are concerned. Okay, now the applications of M sequences, we said yesterday, are primarily in scrambling, because the spreading part may not be, we have not yet found a solution to that. So now how does the scrambling work? If I have a input information sequence SI binary, I can do a modulo 2 addition with my M sequence, which is also represented in the binary form, modulo 2 addition, and this will come out to be a scrambled sequence. Scrambled sequence. Okay, so the transmitter has to generate the M sequence. Now, and then you do the rest of the processing. At the receiver, let us say that you have received the scrambled sequence, you have to be able to unscramble it. And the unscrambling process is basically a modulo 2 addition with the M sequence itself. Okay? So the receiver must also be able to generate the same M sequence, and M sequences can be very long. Yesterday we saw that the long code used in CDMA 2000 is 2 power 42. So where in the M sequence, where do I start? So these two must somehow be synchronized. The receiver must know at this point in time what is the M sequence, what is the phase of the M sequence that is being used for scrambling. That same M sequence value should be added at this point, and this is what gives us the data once again. Okay, this is and I just want to write down something very simple, but I want you to think about this. So Si of n is a binary value. I do the operation with the M sequence. Let me call that as B of n. So this is the scrambling operation. Then at the other end, I do exclusive OR with Bn. Bn exclusive OR with itself will remove the scrambling. So this is the unscrambling operation, and what comes out of this is Si of n. That's what we have written down here. Okay. So again, simple operation, but it's good for us to know in the context. So in a CDMA system, you have to be synchronized at the chip level. Okay, it's much more stringent than a narrowband system, because in a narrowband system you must be synchronized at the symbol level. Chips are much smaller in terms of time duration compared to a symbol, so therefore synchronization at the chip level is critical. Okay. Now an interesting question. What happens if for some reason your estimation of the synchronization is slightly off and you're off by one chip? Okay. If you are off by one chip, if the Rx, not you, Rx, the receiver is off by one chip. If Rx is off, means it is synchronization is slip, it's one off by one chip. What happens? By one chip. Okay. So what we have is Si of n modulo 2 B of n. Okay. Modulo 2 B1 of n, am I correct? You're off by 1, it's shifted to the 1, and we know that B of n plus B1 of n is some other cyclically shifted version, BL of n. So what I actually will get is Si of n scrambled by BL of n. Actually, I'm in deep trouble, because now what happened? Now I don't even know what the scrambling sequence is, because the combination of the original sequence plus a cyclically shifted version, now I actually must figure out what is the shift in order to undo this. So this is where the problem is coming. Okay? So this means that the scrambling is still present, it is still scrambled, and the problem is it's scrambled by a sequence that I did not use, right? It's a new sequence. So it is, and the scrambling is different from the original scrambler. Okay, so it is a important point to keep in mind. So though it may seem like, oh, it's just trivial, just do modulo 2 addition at the transmitter, modulo 2 addition at the receiver. No, the synchronization is very, very important. Okay. Just an observation. Okay. Now this is CDMA 2000. Goes by the name CDMA. CDMA is lowercase. That's the trademark. Officially, code division multiple access actually has the acronym uppercase CDMA. The system, the first system that was used using code division multiple access was CDMA, and then eventually became called CDMA 2000. 4 types of logical channels that need to be supported. One is a pilot channel used for channel estimation. Second is a sync channel, then a paging channel for all the exchange of information between the mobile and the base stations, and then finally the user's traffic. Okay, and we saw how all of these are all will eventually be transformed into a sequence which has this magic number 1.2288 mega chips per second. All these channels eventually must produce 1.2288, and at that rate of 1.2288 they get combined and then pulse shaped and then transmitted using an IQ transmitter. Okay. So in the process we noticed that there were two PN codes or M sequences that were utilized, and the two PN sequences, the official names given, the one is called the short code or the short PN sequence. This is the one with 2 power 15 as the basically 15th order polynomial. Okay. So this will produce a sequence 2 to the power of 15 minus 1, and in the but basically this number is 32767. It's a slightly awkward number. If it had been 2 power 15, it would have been much easier. So they actually make it a 2 to the power of 15 sequence in the implementation. Now what is it that they had to, that basically means they have to insert one bit, and that one bit comes, there is one occurrence of the following sequence: 00014 run length. Okay, there is one run length. Basically, somewhere in these in the sequence there will be a length 14 zeros. 15 zeros can never occur. 14 zeros. So after these 14 zeros, you insert a plus 1. The 1. So this is the bit that is inserted, and so you know exactly where the additional bit has been inserted. So that is after, when you see 14 zeros. That's so this, with this insertion it becomes 32768, and this is used for base station identification. Base station identification. Do a simple calculation regarding this. Because of multipath, I cannot use successive cyclic shifts. We said that we are going to use cyclic shifts by 64 units. So basically base station codes, these base station codes that are used for identification are separated by multiples of 64 chips, 64 N chips. Okay, so N equal to 1, 2, 3 and so on. So how many base stations can be supported? Number of base stations that can be supported, it has to be this 32768 divided by 64, 32768 divided by 64, that comes out to be 512. And they thought that no cellular system or no individual deployment or in one location will require ever need more than 512 base stations. So they say, oh, this is pretty good. We will build a system that is fine. Okay, whether that's so that's a little bit of history. Okay, what about I said there are two codes. One is the short code. The other one is the long code. The long code consists of a 42 shift registers. 2 power 42 minus 1. This is used in the paging channel to scramble. It is also used in the traffic channel with a user specific mask. So it is not just the M sequence, there is some additional modification, and this is also used to tell you where to insert the power control bits. So this long code plays a very important power control bits. Which of those you have to insert 800 of them per second, where do you puncture and insert the power control bits. The locations are determined by the long code, and of course what value you insert depends on whether the base station wants you to increase the power or decrease the power. Okay. So again, so now if you go back and look at this information, this hopefully is a useful. And these numbers also are important. So if you go along this in this branch, so this is being generated at 1.2288 mega chips per second. Okay, when you downsample it by 64, you get 19.2 kilo chips per second. KCPS. Okay, shouldn't write bits. Okay. Then if I further downsample by 24, that's what gives me 800 chips per second. Okay. So, ultimately there is this downsampling. All of these numbers are done using simple operations like downsampling, upsampling, and they all are the way they are chosen has a very specific structure and a purpose behind that. Now, this is CDMA 2000, and any CDMA system more or less will have similar types of information. It must have a way for you to estimate the channel, either a pilot channel or pilot symbols. It must have a paging channel. It must have the traffic channels. So, wideband CDMA has the following difference with respect to a CDMA 2000, and that difference is that all the spreading codes for CDMA 2000, all the codes are from Walsh-Hadamard, or I think I used the notation H6, which means they are length 64 sequences, okay, all of them. Whereas here we are not constrained by the length 64 and there are differences. So, let's quickly build on this and see how to understand this system. Okay, so let me quickly spend a few minutes on the wideband CDMA system, introducing for you one of the key elements of widebands of the wideband CDMA system. So, wideband CDMA also uses Walsh-Hadamard codes, but it uses Walsh-Hadamard codes of different length, not just a fixed length, of different lengths. We make some assumptions about the possible links that can be used. So, Walsh-Hadamard codes you can have are 4, 8, 16, I have left off 2, but basically starting. So, basically you get powers of 2, 64 and on. This is 2 squared, this is 2 squared, 2 cubed, 2 power 4 and so on. So, basically powers of 2. Okay. So, the wideband CDMA does the following. Let us say that there are 2 users, one of them has got a higher data rate. So, user 1 has higher data rate than user 2, higher data rate than user 2. Okay. Now, user 1 and user 2 cannot have arbitrary data rates. So, because the spreading factors are restricted, okay, just one more line before we go to that point. So, this will also mean which of them has got a longer spreading code? User 1 has got a higher data rate. So, we will have a shorter spreading code, the user 2 will have. Okay. So, user 2, this also is another way of saying that user 2 has got a higher spreading factor. Okay. If you have a higher spreading factor and the chips are always fixed in terms of their duration, then the symbol duration of user 2 is longer. Okay. So, user 2 has higher spreading factor. If you have a higher spreading factor, that automatically leads to, because your chips are of constant duration, of longer symbol duration. Okay. I hope just sort of the links between that. Symbol duration. Okay. And so, now the condition is the symbol duration of user 2 divided by the symbol duration of user 1 has to be an integer and it has to be a power of 2, because that's what will be allowed because of these different spreading factors. So, when I take the ratio. So, so typically as an example, supposing user 1 has got the following spreading. Okay, this is T1, user 1's symbol after spreading. User 2 can have this, or user 2 can have this, because it's got a lower rate. It can be a factor of 2 or a factor of 4, and so basically this is very important for us to maintain. We don't allow arbitrary spreading factors, but gives you enough flexibility. But now, very important, how will you construct the receiver? Receiver for user 1 will say, I am going to require the following orthogonality condition. What am I orthogonality? What am I going to do? I am going to do a match filter receiver. what will I use as my duration of my waveform? It will be of duration T1. So again, keep in mind that this is where it's a very simple step, but important that you are following this. So the orthogonality condition, when I have different lengths, is very important for me to capture. Okay, so the orthogonality condition says that I can go from 0 to T1. That will be my it will be G1 of T, G2 star of T plus LT1 dt should be as close to 0 as possible. Now, what am I saying? I have this portion of the waveform and I want to correlate with respect to that. Now, this portion of the waveform must be orthogonal to this, then shift the spreading sequence of user 2 by how much? T1. Then you have to show that it's orthogonal to this portion after you shift. Then you have to show it's orthogonal to this portion, it's orthogonal to this. Okay? And how many such shifts will you get? L? 0, 1, 2, all the way to 2 power k minus 1, because that's the number of possible shifts. So this is the essence of the orthogonality condition. Why? Because the receiver, in order to detect this symbol, will take this portion of the received waveform, will take this portion of the received waveform and apply the correlation based receiver. And therefore, it will have to correlate with this, it will get the desired data. This is some unwanted portion, but this correlation segment waveform must be orthogonal, must look orthogonal to this portion. Then this portion does not affect my decision. Then I move my receiver to this portion, and then I try to do the correlation based receiver. Then, but at this point in time, it has to show orthogonality with this part of the user 2's code, and that's how the whole thing emerges. Maybe it's may find it a little bit intuitive to write it in the following fashion: 0 to T1, instead of shifting, instead of writing it like this, you can write it as G2 star T plus LT1 times G1 star. Okay, G1 star. Okay, maybe this is more intuitive for us to write, because that's how so this we want to be as close to 0 as possible. These two are exactly this. I've just rewritten that. Okay, so now we also in the last class we did a quick saying if I have assigned a code, I cannot assign the any successor and other things. So I want to this technique of preserving orthogonality at different lengths has got a specific name which was introduced for wideband CDMA. It's called orthogonal variable spreading factor codes. Orthogonal variable spreading factor codes, OVSF. And it's an interesting concept, because for the first time we started to think, saying, hey, always it was always thought of as all users having the same spreading factor. Now you may have a voice application which has got certain spreading factor. You may have a high data rate data application which has got a different spreading factor, and both of them can be supported on the same CDMA system. So OVSF is a very powerful concept, and that has been introduced in wideband CDMA. So let me just quickly give you an introduction, or basically so OVSF, the concept says that we can use codes of different lengths, codes of length, and the lengths are constrained to be powers of 2 power k. So starting from k equal to 2 onwards we can go, and we still have to maintain orthogonality. Orthogonality maintained even with codes of different length. Orthogonality must be maintained, and that's the feature of OVSF. Orthogonality maintained, you can please add to it saying that for codes of different lengths. So the rule is a very simple one, OVSF rule. The rule says that if a code is assigned, then you cannot assign any of its successors. That's the first thing that is forbidden. You cannot assign any of the successors. You cannot assign a successor. That means a code of longer length that is derived from this code. So this is a code of longer length. A successor will have longer length, a predecessor will have shorter length, and you cannot assign a predecessor either, because both of them will violate a predecessor. Predecessor. This is a code of shorter length. Okay. So this is the basic rule. You can assign everything else. All other codes, any other code can be assigned. Any other code can be assigned. Okay. Now, when you have codes of length 4 or 8, it's easy to do it by hand. But usually the spreading factors in wideband CDMA go up to 512. Okay, you can go up to. So basically, these codes, you have to have a systematic way of numbering the codes. So the convention that is used in terms of the notation. Okay, notation. This will help us in the next example that we are going to. So OVSF L comma N means this is the nth code of length L. Of length L, where L is some power of 2, okay, and N itself can be 0, 1 all the way to L minus 1. Okay, so nth code of nth code of length L. Okay, now the Hadamard way of generating longer length sequences from the shorter length is captured by the following. So OVSF length L comma 2I, that means I am looking at some the length L, the 2ith code. This would have come from an OVSF of length L by 2, okay, and it would have come from the ith code of length L by 2, because when I go to the next level I will get 2, 2 for each of those. So and how was this generated? I got it by repeating OVSF L by 2 comma I. L by 2 comma I. Okay, so that was how I got OVSF L comma 2I. Now OVSF L comma 2I plus 1, that is obtained by OVSF L by 2 comma I minus of the flipped version of OVSF L by 2 comma I. Okay, so I hope if you just try a few write it down, it's not difficult at all to see. In fact, especially if you go back to the tree that we drew, it will become very clear to see that 4 comma 2 will generate 8 comma 4 and 8 comma 5. You can see that, and then you can verify this. Okay, so just as a quick example, as always, let's say OVSF 2. OVSF 4 comma 2. Let me just see what OVSF 4 comma 2 is. 4 comma 2 is 1 minus 1, 1 minus 1. OVSF 4 comma 2 is 1 minus 1, 1 minus 1. This will give me OVSF 8 comma 4. That will be 1 minus 1, 1 minus 1, and then that repeated 1 minus 1, 1 minus 1. And it will also give me OVSF 8 comma 5, which will be 1 minus 1, 1 minus 1, minus 1, plus 1, minus 1, plus 1. Okay, basically that sequence flipped. So again, from here we have obtained this set using the formula that is given on the left. Okay, now comes the design of the system. Wideband CDMA system, just like CDMA 2000, has followed certain conventions for assigning. So OVSF 256, 0 is always dedicated for the common pilot channel. Common pilot channel. Okay. OVSF 256, 1. OVSF 256, 1 is dedicated for control channel, so is OVSF 256,2 and OVSF 128,2. Okay, these three are dedicated for what we call as the control channels. Control channels include synchronization channel, it includes the paging channel and so on. Okay? Dot dot dot. Several control information has to flow. Now, why would somebody use a spreading factor of length 256 and a spreading factor of length 128? What does this tell you? This particular channel has got higher data rate. So, in order to accommodate the higher data rate, they said, okay, instead of keeping adding more and more channels, I'm going to use 128,2 and then send it in a more compact fashion. Okay, so this is structure. Now, how do we visualize this? Okay, so this is how we visualize. So 256,0, the predecessor was 128,0 and its predecessor was 64,0, predecessor 32,0, predecessor 16,0, predecessor 8,0, predecessor 4,0. Okay? So, and of course 128,0 also is the predecessor for 256,1 and 256,2, the predecessor is 128,1 and this one has got 256,3 and so on. Okay? Now, very important to note, you have, when you assign 256,0, when you said that's for the common pilot channel, that automatically eliminated all predecessors. X means that they cannot be used in that system, in the wideband CDMA system. That's the OVSF rule, right? Can 256,1 be used? Why? Because it is neither a predecessor nor a successor. Okay? So this is okay. 256,2 can be used. So 128,1 cannot be used. What is the predecessor of 128,1? 64,0. That anyway that was already blocked out. Okay? Now 128,2 is 128,2 has been used. So 128,2 has got two successors, that will be 256,4 and 256,5. Okay, the predecessor of 128,2 happens to be 64,1 as the predecessor, and the predecessor of that will be 32,0. Okay, so we assigned 128,2. That was the fourth code that we have assigned as part of the system design. So, which means that I have blocked 64,1 and all the predecessors. I have also blocked 256,4 and 256,5. Okay? So, this is the wideband CDMA code allocation scheme. So, now comes the application of this. So, this is the length of the code, and this is the number of codes available. Okay? Now, if I tell you I am interested in length 256 codes, how many 256 codes are available? So, I go down the length, the line of 256, and if there is either a tick mark or an into mark, that means it's gone. Either it's been assigned or it's been blocked. So, 5 of them have been blocked. So, the number of codes available will be 251, 5 of them. So, if I go down to 128, I see that 3 of them have been blocked. So, 125 codes are available. So, go down the list, 64 length, you get 62 of them available because 2 of them have been blocked. 32, I can have 31 codes used, and for 4, I can have 3 codes used. So, this is what is available. So, if a user comes and says, I want length 256, no problem, I have got 251 of them available, I can assign to you. You want length 32, I have so many codes available. So, you are constantly mapping or managing the allocation of these codes. At any time, if you have assigned one code, you must block out all the successors and the predecessors. That's the most important thing, because if you don't do that, then you will violate orthogonality and the performance of your system will go down. Okay? So managing the, and once you have a map like this, and all you have to do is put the tick marks and the X marks, and then you can, when you actually write it as a program, this is very easy to handle. Okay? Now, just for you to try out, if this particular code had been replaced by, instead of 128, 2, let us say that I had assigned 128, 127 instead of. Can you please redo this calculation? With this green allocation, what are the number of codes available? Okay. It's just a slightly different calculation. A different set of codes will get blocked, especially if you do 128, 127. Some other codes will get blocked, and interesting for you to see which ones will get blocked. Okay. So please try that. We will pick it up from here in tomorrow's lecture. Thank you.